Now we are going to find out the expression of magnetic field due to a toroid. Now what is a toroid? It is just a solenoid of finite length which is bent in circular shape. So if you take a solenoid of finite length and you bend it in a circular shape and join the free ends, the two ends of the solenoid are joined, that becomes a toroid. So in other words, we can define the toroid as a non-conducting ring. So we have shown the non-conducting ring over here with yellow color. So the non-conducting ring around which wire is wound. So around this non-conducting ring wire is wound. So that becomes a toroid. Now to find out the magnetic field due to a toroid, we consider an ideal toroid of n number of turns. Now what is an ideal toroid? Ideal toroid is the one which is tightly wound and has uniform spacing between the turns. So which is tightly wound and has uniform spacing between the turns, that is called as an ideal toroid. So we consider an ideal toroid which has n number of turns in total. So there are total n number of turns. Now we want to find out the magnetic field at any point inside the toroid. So let's say if you want to find magnetic field at this point inside the solenoid, inside this toroid. So I have drawn the same diagram over here. So over here you can see that the current close to the inner edge of the toroid, means close to the inner edge. This is the inner edge of the toroid. So close to the inner edge, at this inner edge of the toroid, you can see that current is directed towards us. So it is pointing in the outward direction. Therefore, here I have shown the current by dots because it is coming outside the paper. And the current on the outer edge of the toroid is directed inside the paper. Therefore, I have represented it by cross. And we want to find out the expression of magnetic field inside the toroid, means over here, let's suppose, means at this point P. So we will be finding the expression of magnetic field in this article using the Ampere's circuital law, and we already know that to use Ampere's circuital law we must draw a closed path. So in this case also we will draw a closed path. So we will draw a circle which passes through this point P and whose radius is equal to small r. So this observation point P, where we want to find the expression of magnetic field, is at a distance of r from the center of the toroid. So we will draw a closed path, we will draw a circular path which passes through this point P and which has a radius of r. So here I have drawn a closed path. Let's represent it by C. And we are moving in this closed path in the anti-clockwise direction, means in this direction. So we will use Ampere's circuital law for this closed path. So for this closed path, we will have line integral of magnetic field over the path C will be equal to mu naught times the net amount of current which is enclosed by this closed path. So here let's suppose that in each turn I amount of current is flowing. Now how to find the net amount of current which is enclosed by this closed path? So for that you can easily see over here that for n turns in this whole toroid, what are the number of turns which are crossing this closed path? So the turns which are passing through this area which is enclosed by this circular path C, that is just equal to capital N. So capital N are the total number of turns which are present in this toroid, and in this whole area enclosed by this circular path C, so in this whole area capital N number of turns are passing through this area. So what will be the net amount of current which is passing through this closed path? That will be equal to capital I times the number of turns. So net amount of current which is enclosed by the path C is just equal to number of turns, that is capital N, times current which is flowing through each turn, and that is capital I. So the right hand side will be equal to this. Now we will be solving the left hand side. So we have line integral of magnetic field over a closed path C. Now according to the symmetry of this toroid, it is clear that the magnetic field lines inside the toroid, due to the current in the toroid, will be in the form of circles. The magnetic field lines will be in the form of circles which are concentric with the toroid. So at this point P, the magnetic field will be pointing in this direction, means it will be tangential to this circular path, as well as dl vector, the length element, will also be directed in this direction. So for the case of toroid, if you are finding magnetic field inside the toroid, the magnetic field and the length element are directed in the same direction if you are taking a circular path. So you can solve this one. You will get magnitude of the magnetic field times magnitude of dl vector times cos of 0 degree, and that will be just equal to 1 is equal to mu naught times n times capital I. Now at all these points they are at the same distance from the center of the toroid. So at all these points the magnitude of the magnetic field will remain the same. So this magnetic field B magnitude can be taken outside the integration. So that will be equal to B into line integral of dl over this closed path C, and that is equal to mu naught times n times I. Now what is this integral equal to? So we have the integration of dl over this closed path C. So that will be just equal to circumference of this circle. So this integration will be just equal to, so B as it is times the circumference of this circle, that is equal to 2 pi r, and that is equal to mu naught times n times I. Now from here you can find out the magnitude of magnetic field will be equal to mu naught n times I divided by 2 pi r. So you can clearly see that as the distance of the point P from the center of the toroid increases, means if you are moving from this point to this point, the magnetic field will decrease. So as R increases, the magnetic field decreases inside the toroid. So close to the inner edge, so this is the inner edge of the toroid, close to this edge magnetic field will be more, and as you are moving towards the outer edge, the magnetic field will decrease. So if Ri is the radius of the inner edge, so this edge is at a distance of Ri from the center of the toroid, and Ro is the radius of the outer edge, the magnetic field is least at the outer edge, means it is less at the outer edge, and it is maximum at the inner edge. So on the outer edge the magnetic field will be least, and on the inner edge the magnetic field will be maximum, because magnetic field is inversely proportional to r, which is the distance of the point from the center of the toroid, and this expression is valid inside the toroid. Now what if the toroid is, the cross section of the toroid is very small, means this turns, the cross section of these turns is very small. In that case Ri and Ro will be approximately equal. So if the cross section of the toroid, of each turn of the toroid is very small, then the radius of the inner edge and the radius of the outer edge will be approximately equal. So we can neglect the variation in R. So in this particular case, as you are moving from inner edge to the outer edge, the R is changing. So R is changing as you are going from the inner edge to the outer edge. But if the cross section of each turn of the toroid is very small, then we can neglect this variation in R and we can consider R as the average radius of the toroid. So R will be average radius. Then what will be this 2 pi R? So if R is the average radius in that case, then this 2 pi R will be the mean length of the toroid. Mean length of the toroid. So 2 pi R is the length of the toroid. So if R is the radius, if R is the mean radius, if R is the mean radius, in that case 2 pi R will be the mean length of the toroid. So in that case we can call n divided by 2 pi R as the number of turns in unit length. So in that case, when the cross section of the toroid is very small, in that case n divided by 2 pi R can be called as the number of turns in unit length of the toroid. So this can be written as small n in that case. So this is the general formula of the magnetic field inside the toroid. But if the cross section of the toroid is very small, means Ri and Ro, they are approximately equal. In that case we can neglect the variation of this R, and hence this 2 pi R will be the mean length of the toroid. So n divided by 2 pi R can be put equal to small n, which is the number of turns in unit length. So thus we can see that the magnetic field inside the toroid has a constant magnitude if the cross section of the toroid is small, and if the cross section is not small, in that case the magnetic field close to the inner edge is more, and as you are moving towards the outer edge the magnetic field will decrease. But if the cross section is small, in that case the magnetic field will be constant. Now in the same way you can find the magnetic field for the points which are lying outside the toroid. So let's say if you want to find magnetic field at this point. So the same thing will be done over here. To use the Ampere's circular law, we will draw a circular path around this toroid whose radius will be equal to R1, let's suppose. So R is the distance which we have taken over here. So let's suppose this point is at a distance of R1. So to find out the magnetic field at this point, we will draw a closed circular path which passes through this point and whose radius is equal to R1 and center is at O. So the circular path which we are going to draw in this case will be of radius R1 and its center will be at O point. So when you will be finding the net amount of current in that case, so here also you will use the same Ampere's circular law, and that will be line integral of magnetic field over the closed path will be equal to mu naught times the net current which is enclosed. So for this circular path which you are going to draw, for this circular path, what will be the net amount of current? Net amount of current will be equal to 0, because you can see that if the current is directed towards you, then the same current is directed away from you at this point. And similarly for this turn of the toroid, if the current is directed towards you, then the same amount of current is directed away from you. Means the number of turns, the number of current wires in which the current is flowing towards you, the same number of current wires are present in which the current is flowing away from you. So net amount of current which is crossing this area, which is crossing this whole area enclosed by this closed path C, that will be equal to 0. So in that case B vector dot product with dl vector, its integration over the closed path will be equal to 0. So at these closed paths the magnetic field will be equal to 0. So if this line integral is equal to 0, So magnetic field in that case will be equal to 0, and similar thing can be done when the observation point is present over here. So for this case also you will draw a circular path like this, and according to the symmetry of this toroid, the magnetic field, if magnetic field is present, that magnetic field will be tangential to this circular path, and similar is the case over here. If the magnetic field is present, that magnetic field will be tangential to this circular path. So for this closed curve which is present over here, which is crossing through this point, this equation will become B vector dot product with dl vector is equal to 0, because net amount of current which is crossing this closed path is equal to 0. So if magnetic field is present outside the toroid, that will be directed tangentially, that will be pointing tangential to this closed path. So dl vector is in this direction, and magnetic field, if magnetic field is present, that will be also directed in the same direction because of the symmetry of this system. So this B vector dot dl vector will be just equal to B into dl, and cos of 0 degree, that will be 1. So from there you can see that B will come out to be equal to 0. And similar is the thing when the observation point is present over here. So you will draw a circular path whose radius is equal to, let's say that is R2, and center of the circular path is at this point. So if magnetic field is present, then according to the symmetry of this system, magnetic field would be tangential to this circular path, and dl vector will also be in this direction because we are moving in the anti-clockwise direction. So the same formula will be valid for this curve also. And in this curve, the net amount of current which is present in this closed path is obviously equal to 0. So this equation will also come for this curve as well. So in that case also B will come out to be equal to 0. So magnetic field at all the points which are present over here and at all the points which are present outside the toroid is equal to 0, and magnetic field is finite only at the points which are present inside the toroid, and that magnetic field is given by mu naught capital N into I divided by 2 pi r. And if the cross section of the toroid is very small, in that case magnetic field will come out to be equal to mu naught N into I, where N is the number of turns in unit length of the toroid.